All right, so good afternoon. My name is Matthew Tarver. I'm a senior ocean engineering major here at the University of Southern Mississippi. Today I'm going to present on my autonomous surface vehicle I built for OE 497 Ocean Engineering Capstone project. So a quick overview of everything I'm going to cover today. So first we'll talk about autonomous boats. What are they and what are they used for? A brief project description, a motivation for this project, the minimal viable product and my aspirational goal, how it works, and I'll cover step by step the process of designing and building, a brief video demonstration of the project, skills used and learned, and acknowledgments. So autonomous boats are used to extend the reach of human operators and to help increase situational awareness. Currently, autonomous boats are being used for observation in military applications, hydrographic surveying, trash and oil spill cleanup, and environmental data collection. Autonomous boats provide cost-saving ability by replacing crewed vessels or assisting crewed vessels. So, for example, if a hydrographic surveying company is hired to survey a large area for future wind farm development, the amount of time spent at sea can be reduced by deploying multiple autonomous boats to help cover area. This saves money by reducing fuel consumption, labor cost, maintenance from wear and tear, and less strain on logistics. So notice the image on the right is the Sea Hunter. It is designed by Leidos for the U.S. Navy. It's a 132-foot long trimaran operating at a cost of $15,000 to $20,000 a day compared to $700,000 a day for a destroyer. It's currently being used and tested by the Navy for anti-submarine and warfare observation. So a brief project description. So my goal was to build an autonomous boat using open source drone software, ArduPilot, and off-the-shelf drone hardware typically associated with flying drones, using a handheld controller to operate the vessel instead of a computer for ease of operation and mission planning, and to be able to build a low-cost drone. So my motivation for this project stems from existing work experience. While attending school here at USM, I secured an internship with a company, United States Marine Inc. I've currently been there 2.5 years, working from an intern to a drafter to an electrical engineer. So my time there has introduced me to a general interest in autonomous systems. And by choosing to build an autonomous boat, it allowed me to develop other skills I was interested in, such as electrical design work, hardware and software integration, control systems, and communication protocols. It also allowed me to really understand how much is involved in building a system like this. You really can't comprehend how much is involved in the development of an autonomous system until you start building one. So for example, things to consider are speed and power requirements, propeller design and how it affects the way the vessel travels, hull design, your longitudinal center of gravity and weight help determine how the vessel sits and travels through the water. Different aspects of mission planning, including waypoint sizes. Does the vehicle turn into a waypoint or after it passes through the waypoint? And safety and liability. So my minimal viable product and aspirational goals. So my minimal viable product would be to have a handheld controller to act as a ground station for the purpose of mission planning and displaying telemetry control data such as speed, direction, and location. The autonomous surface vehicle would be capable of autonomously traveling the set waypoint, loiter, and to return home. My aspirational goals was to be able to incorporate some degree of obstacle avoidance along with a companion computer to increase decision making and route changing. So a hardware overview. So there are 7 main components to this autonomous boat. So you have a controller, your hull or frame, power source, power distribution, GPS, communication, propulsion. So to start, so first, for most autonomous systems, they use just a controller, whether that being an actual onboard computer. In my case, I used a cube orange flight controller. So next we have a power source. I used 4 11.1 voltage LiPo batteries in parallel, each with 5.5 amp hours. The reason for this is they're lighter and they provide a higher energy density. Next, we have power distribution, which includes a power distribution board and 2 DC to DC buck converters, which drops the 11.1 voltage down to the required voltage to power the various components on board. Next, we have the HERE 3 GPS unit, which provides location and heading. Then we have our HereLink transceiver. The HereLink transceiver provides telemetry data to the handheld controller so that I can see the vehicle position and orientation, along with different traveling parameters such as speed, pitch, roll, and elevation data as the vehicle travels. The handheld controller also allows me to change settings and plan missions to send to the vessel. And next we have the brushless motor that provides propulsion. And so just a little closer look at some of these components. So you have, in the top left, you have your stern drives and brushless motor assembly. In the top right is my HERE 3 GPS. The bottom left is my HereLink controller and telemetry unit. This is what allows the controller to communicate with the vessel. In the bottom right, I have my Cube Orange flight controller. So the first major step to building this vessel was calculating power requirements. This is important for several reasons. First, I had a desired speed of 1 meter per second. The reason being safety. If I lost control for any reason, I didn't want the boat to crash into an obstacle and damage it or someone's property. So I used two equations. To solve the power requirements. First, I used the power equation. So power equals force times velocity, and the drag force equation. I got my force using the drag force equation. FD equals half times rho times velocity squared times CD times the wetted area, and my velocity was calculated in a range from 0 to 3 meters per second. And so you can see, so for my drag force equation, my values, I had half times 1,035 kilograms meter cubed, which is the density of salt water, times my velocity, times 0.04, which is my drag force coefficient, and we'll talk a little bit more in depth about how I got that number, times my wetted area. And I came up with a value of 8.2 watts is what I needed. So to validate the power requirements, a still water test was conducted. A still water test works by attaching a load cell in line with the hull and towing it at various speeds, therefore providing you with the force and velocity. So the original purpose of the 6-foot hull was for a tow tank test. The hull is a model of the Mark V patrol craft built by United States Marine Inc. USMI had the hull sent to the Davidson lab run by the Stevens Institute of Technology for testing. After I'd already conducted my still water test, I was able to gain access to the data collected from the Davidson lab and compare it to what I had collected. And so here's a demonstration of the 6-foot hull traveling in the Davidson lab tow tank. So for the still water test I conducted, it was conducted off the coast of Gulfport, Mississippi, in a canal on Cat Island. This location was chosen because the canal had virtually zero boat traffic. It was mostly blocked from the wind and had no waves. This helped to eliminate as many environmental factors as possible. Using a rod mounted off the side of the boat, I was able to tow the vessel at the side of the boat. I used a Pascal load cell connected to my phone through Bluetooth and relayed data back to me while we monitored speed from a handheld GPS unit. We had 4 separate runs so we could average out the data as best we could. So I used MATLAB to plot my data and process everything. So the following graph shows the 4 separate runs I made along with the average and the data collected from the Davidson lab. There were 2 major differences between my data and the Davidson lab. So first, I used a drag force coefficient of 0.04. I came up with this number mostly from research, trying to figure out what the standard is for planing holes, which is what I have, and that's the number I came up with. Because I started this process before I got the data from the Davidson lab. But the Davidson lab used a drag force coefficient of 0.01867. And so comparing this data, I was able to confirm the 8 watts of power I calculated. So next I moved to propeller design. So there are 13 parameters considered when choosing a propeller. The first 6 must be specified for every design, while 7 through 13 are important for solving specific design problems, according to the propeller handbook I used. So in order of importance, you have diameter, pitch, number of blades, the hand, so left or right hand turning, the propeller shaft diameter and keyway, and the blade area. or the 6 that I covered. And that's all I needed for the scope of my project. So propeller design. So I started out with just looking at the number of blades. So a 4-blade propeller was used because of the following characteristics. It provides better handling at low speeds. It has a better holding power in rough seas, and it provides better efficiency than any other propeller type. And since it's an autonomous boat and it's battery powered, that's what I wanted, efficiency, so I could stay out there longer and continue testing. So since 2 stern drives were used, the hand of the propeller was opposite, so the vessel did not shift from side to side. And so you can see in the image on the top right a demonstration of what I'm referring to. And the propeller shaft diameter was determined based off of the stern drives already used. So the diameter of the propeller is the full distance from edge to edge, while the pitch is defined as the distance of a propeller would move in one rotation, similar to a screw going into a board. So to help solve for the diameter and the pitch, I used MATLAB so that I could calculate different variables easier. I basically set everything up so it was plug and play. And so again, I referred to the Propeller Handbook by Dave Gurr. And using the provided equations, solving for the SL ratio, I was able to determine the ideal diameter and pitch. So my diameter was 2 inches and my pitch was 0.1 inch. And so a quick demonstration of how important this is. You can see in the first video the amount of cavitation that you can see. Compared to the next video. And so next I began the process of outfitting and actually building the vessel. So the first step was lamination. And so the hull was built from balsa wood. And due to the soft, pliable nature of balsa, I chose to laminate the hull to protect it from waterlogging and damage. And so you can see from the top image is how I originally received the hull from USMI. So my first step was sanding the paint off, as you can see in the second image. So next I used Bondo, which is a type of resin infused with strands of fiberglass. I used this in the keel of the boat to help add weight for better stability and to round off sharp edges to help the fiberglass mat lay smooth. I then conducted what was called a wet layup, where resin is painted onto the vessel and then a fiberglass sheet is laid in position and resin is brushed onto it to seal it. And so I sealed the entire boat inside and out to help protect it. Next, I faired the boat. So fairing is the process of filling in low spots and sanding high spots down to create a smooth surface. This helps reduce drag on the boat and creates a clean surface so that it can be painted. And then finally, I sealed everything with primer. So after lamination, the first component outfitted was the stern drives. Using SolidWorks, I created a template to help with the alignment. I had the template cut out in the USMI machine shop using a CO2 laser. I then installed a deck inside the boat to mount my electronics onto. The reasoning for this was if the water somehow gets into the boat, it would settle out on the bottom and give me some degree of buffer zone to protect my electronics. And finally, I installed a polycarbonate top deck with inserts to so I could tighten the deck down and squeeze it. And compress a gasket to seal the boat. And so my water proofing did work. I had 0 issues with water getting into the boat throughout the testing. So outfitting and electrical, here's a quick demonstration of my motors running, along with my servos turning my stern drives. So I did have some issues during the install and outfitting everything. So while installing hardware and testing, I began having issues with my GPS not connecting, and my laptop would disconnect from Wi-Fi if I got too close. And so the problem was the electromagnetic interference. So I isolated the problem to the DC to DC buck converters. I used a cheap set from Amazon, and so I ended up swapping them for a higher grade converter. And I moved my power distribution system and my flight controller to fiberglass boxes coated with copper paint. And this virtually eliminated any issues I had. And so starting from left to right, you can see you can read my electrical schematics, so I'm going to briefly go over it. So I used 4 11.1 LiPo batteries in parallel. So they go through my voltage monitor and power distribution board. From there, my 2 DC to DC buck converters on each side of the power distribution board drop down the voltage to an acceptable level to power my telemetry unit, which you can see here, and my flight controller in the center. And so the power distribution board also feeds the electronic speed controller. The ESCs here, they get a pulse width modulation signal from the flight controller to control speed, and you can see a detailed pinout in the bottom left-hand side of how everything works. So sea trials and testing. So for operating the vessel and mission planning, I use Qt ground control on the handheld controller. Initial trials were plagued with alignment issues with propulsion and poor calibration, and it took a lot of time to get to the point that I could even begin tuning the vessel and understand what was happening. And so, for example, you can see this test run in which you can hear grinding and the drive sees up and it cuts the vessel off. And so you can see in the bottom left-hand side an exploded view of the stern drives in the diagram. So despite good reviews on the drive, I had continuous problems with them through the entire project. The gears are held in place on shafts here and here by individual set screws that tend to want to back out, and the shafts and gears would constantly bind. So I did get it to an operational point where I could begin testing it. So here's a short video of a run afterwards. And so this is just a simple waypoint and return. It only goes out 15 or 20 feet and then just circles back around. Just simple testing, moving ahead. Sorry. So the flight controller on board acts like a black box, similar to that on a commercial airplane, and it records the flight data continuously. And so using Mission Planner, you can download that data to a laptop and display the various parameters along with a map showing the travel path of the vehicle. And so that was extremely helpful throughout this process. And so the mission shown is a simple waypoint and a loiter mission in which the vehicle travels out to a set waypoint and remains over the position. It might be difficult to hear from where you're sitting, but you can hear the propeller slow down. The vessel slows down as it approaches the waypoint. Notice the ripples in the water. The wind is blowing against the vessel towards me, and so once it gets to the waypoint, it turns and points the bow into the wind to try to hold position. And so the image on the left, you can see my final product painted and demonstrating here on USM campus. So I'm going to move ahead now. Skills and lessons learned. So technical knowledge, circuit analysis, which I took with my degree program, and hardware integration were critical skills. A better understanding of naval architecture and boat building. MATLAB and SolidWorks, which is also taught within USM's ocean engineering program, was extremely helpful. Soft skills, project management, researching new ideas and forming a plan or designing an experiment to solve a problem. And communication, because throughout your senior project here at USM, you're expected to present your research and work with your professors and understand problems and come up with solutions to solve them. And so that was a critical skill, being able to come in every week and discuss what I learned and discuss the problems I had and work through those. What surprised me the most about this project was how complicated a seemingly small project can become and how many small details must be accounted for. So acknowledgement, special thanks to United States Marine Inc. for donating the Mark V hull and funding this effort. Clay Dubois, my senior engineering supervisor at United States Marine Inc., and Bruce Watts, a coworker, for guidance building the vessel and access to testing grounds. And my engineering professors here at USM, Dr. Giro Newts, Dr. Mahdi, and Dr. Kamal, for their guidance. And so here's my references I needed throughout this project, including some of the books I used and referred to. And any questions?
The propeller looks a little shallow, isn't it?
I don't think they were.
What looks shallow? The propellers.
The propellers?
Yeah.
Shallow like a fish?
No.
Like being too high in the water.
High in the water.
Or not deep enough?
Yeah.
They were under the water, probably an inch.
The biggest were the old propellers, so, right?
Yeah, it was comparing the old propellers to the propellers, like after I went through and studied the different parameters of a propeller and understanding it, and
It was
like
both propellers. It was the old set and the new set.
that's correct. Yeah,
Switching back and forth.
yeah. So I wanted a video demonstration of the difference that they can play and how. Because when I started doing the propeller design, I was like, oh, this is wasting my time. I don't want to learn about this. And then when I saw it, I was like, ooh, I'm glad I learned about that. It was really important. So.
Any questions from the audience?
So where do you hope to take the project from here? You hope to never see it again? Or
No. If anything, I'd say I have a renewed interest in autonomous systems. Definitely, but I have a better idea of how complicated and how much can be involved in it. When you think of an autonomous boat, for me, I was like, all right, well, I'm only interested in this small aspect, like control systems and things of that nature. But you have to know how everything works. You can't design a control system for a boat if you don't know and understand how it travels through the water.
About this one?
So I actually kind of started doing some of the research, and I pretty well started from zero as far as what I knew about ArduPilot and these systems. So last November, so a year, 2 or 3 months is about how long it took. Yeah, and I would say, especially you guys who haven't gone into this yet, so your engineering senior project is supposed to solve or answer some question. And my recommendation to you would be, because if your interest is origami, I promise it's going to take you a year. You're going to understand everything about it before it's over with. So definitely pick something you're interested in and something that you want to learn about, something that'll help you. Because I promise they'll find the problem. You just tell them you're interested. You're going to spend a significant amount of time on this project a week on top of your other classes. So I would say make sure you're interested in it. It'll help.
What was for you, out of all the processes that you went to and all that, what was the hardest?
As simple as it sounds, probably the thing I struggled with the most was calculating the power requirements initially, because my background, I'm a welder by trade, and my background is building and construction, and so that's what I tend to fall back on, whereas you literally go through an engineering program to kind of get above that. Not that it's bad, but you should be able to, it's not all about building. You have to understand why you're doing what you're doing, and that's the thing I have to stop myself personally on. Doing the research, understanding why you're doing this, what's happening, and then you can go forward with building the project. That was probably the biggest lesson for me that I learned, and it's significantly shown in my own personal work experience. So working at USMI, I'm working as an electrical engineer. So one of the biggest jobs I had here recently was integrating 2 engines into the vessel. So everything electrical to make these 2 engines work with the boat. So my total budget, this project ended up costing $3,275. What's actually on the boat, I actually lost $800 on the project, and almost every dollar of it could have been saved through better research. And so that project at USMI, integrating 2 engines into a boat, I think I lost $30 in parts. And that was because I accidentally sent the wrong link to purchasing. So, lessons learned. It's better to learn it here, and as hard as it is to go in there on a weekly basis and receive feedback, and sometimes you get beat down and sometimes you get applauded, but it's better to get the feedback here versus going to work and getting feedback from management that you did bad. So it's pretty important.